Today I have the pleasure to introduce Professor Eliška Greplová. So Eliška is an associate professor at the Kavli Institute of Nanoscience and Quantum Nanoscience. She's recently appointed a group leader at QuTech, for which we are very happy. She has worked at AI for Science, Microsoft, ETH Zurich, Aarhus University, Max Planck Institute of Quantum Optics in Munich, and she now leads the Quantum Matter and AI research group here at TU Delft. So she works at the interface of very exciting fields, and we can probably see that by the volume of the audience here. So it's working in quantum technology, in AI, and in condensed matter physics. So today, I guess we're going to hear a lot about exciting stuff about that. So this floor is yours now.
Thank you so much, Carlos, for a great introduction. And thank you, everyone, for coming. I hope we can spend fun and productive hour together. So as Carlos mentioned, this is my group, QMAI. I want to thank all of them before even starting the talk, because I will show you a lot of the great stuff they are all working on. So if someone just rolls in here and goes like quantum computing in the age of AI, maybe something like this comes to mind. We are now living in the time that there is a lot of hype around these topics, and there is a lot of, anthropomorphization and a super intelligent robots and things like that. But maybe before we unpack all of this, let's take like 10,000 learning steps back and go back to physics. So who here knows what is this? Who has heard about Ising model? Perfect. Most people, right? So it's one of those things that if you do a physics undergrad, you are going to learn what's a phase transition on this square lattice where spins are either pointing out, blue, or down, orange. And you will learn in that course that these models are described by a Hamiltonian that looks like this. We don't need to worry too much about the notation if you are seeing this for the first time, even though most of you don't. What this Hamiltonian just tells you is that if the spins are next to each other, the energy of the system is determined by this formula. So if I have up and up, +1 times +1, multiply by -j, I get energy -j. If I have this, +1 times -1, multiply by -j, energy +j. This is just tells me if the spins are aligned or misaligned. It gives me the formula to calculate the energy, right? You more or less remember this. I see people nodding. So let's do a fun, quick exercise. Which of these has the lowest energy? I hear B. Does everyone agree with B? And why B? Perfect. And so you actually did something very smart, right? You didn't write to use this Hamiltonian and actually write all the pairs and calculate the +j's and -j's for each of these configurations. You just understood from what we were saying before that I need the least of this, not to push the energy up too much, right? So awesome. So we even like this, we can do a very simple, like learning from data tasks. In this model, once you start adding temperature, you have something called Boltzmann distribution that tells you the probability of every configuration at every temperature. What this just says is that if you start adding temperature into your system, the difference between this and this starts getting smaller and smaller. And the more temperature you add, the more you might see that the temperature-driven phase transition happen in this system. As the difference between the aligned and misaligned spins is getting smaller and smaller, the system will not tend to sit into this fully aligned state, but it will cross into some phase that is fully misaligned. And you can even calculate, that's why we teach this model in the first statistical physics course, what is the critical temperature where this phase transition happens. Maybe you also remember that it was a slightly lengthy and annoying calculation to do, but you can do it if you understood all the physics that we teach you properly. Now, let's forget about Hamiltonians and phase transitions for a second And I like to show this slide in almost all of my talks because I think this is the coolest, really. In 2016, Lei Wang took these configurations that I was just showing you, up and down the squares, and used a very simple clustering algorithm. And I will tell you in a second how it works. But for now, this is the result of that clustering. If I take this big data set and project it into the two axes, I already see that there is some red blob in the middle and high temperature, and the two blobs on the side that correspond to the low temperature, as you can see on a temperature axis. Who has heard about principal component analysis? Some people, but not everyone, but I see that a lot of people are familiar. Basically, if I have data, I can just find the directions where the variance is the biggest, and that will be by new coordinate system. And what I then do is that I can just rotate the data into that coordinate system. With these blue points that I just prepared to illustrate the principle, it doesn't do anything interesting. But if I take my Ising configuration, put them as a column vectors, put them into the axis, into the matrix, and do this axis rotation on that matrix and project into 2 dimensions, I am going to get a plot like this. And I didn't need to know like what's a renormalization group. I can even go as far and check the color of these points that are in between the two blocks and estimate here 2.25. If I substitute the constants into this formula, I get 2.27. So we now understood something pretty profound just doing the simplest clustering algorithm there is. Just to make sure that we all understand why is there the 2 blue blobs in this plot, not just one? Anyone can tell me?
Up or down?
Yeah, perfect. This state and this state, they are the same. Thank you. Okay, so it's solved, right? I will just go around, do the PCA and like get a tenure and everything is awesome. Is there some problem with this logic that anyone can already foresee? Can I, for every problem there is in physics, just change this coordinate system, do the 2 color blobs and be done with it?
So you don't have data for every problem.
That's a great point. Is there some point with this just axis rotation itself that anyone can think about?
Were dimensions interesting?
That's another thing. Okay, we have 2 great guesses, huh? I heard someone saying something. No?
But that's fine.
No, actually, you already started saying.
No, but it's fine, maybe more than 2 dimensions, no? You just do PCA in multiple dimensions.
Yeah, you could. So do we have more conceptual problem with this? Someone else in my postdoc, please, come on. Okay, then we don't. Then we just continue and see where we get. New Hamiltonian. Okay. It's the same as before. Now it looks slightly less familiar because now I am not just doing the nearest neighbor, I am doing the 4 nearest neighbor. I take a placket like this, I multiply it. If the placket is even, for 2 up, 2 down, or something like that, I get a lower energy. If the placket is odd, I get extra minus from this term, higher energy. Same like we did before, except it's now 4 spins instead of 2, right? So very simple. So now which one of these has a lower energy? Yes. Are you guessing or
Visual intuition.
Visual intuition? Does anyone have like a more profound reason? Yeah, please.
Points of the line at that term in the energy.
Say again.
If you make close paths with the same orientations, close paths have lower energy than higher.
Okay, so you know Wilson loops, amazing. But okay, so Indeed, here in this one, I flipped some spins that give me, and thank you, I will come back to the Wilson loop in a second. That would give me the odd thing. But already now, even if you know what the thing that you are supposed to look at is, it's not so easy to look at this one, right? And now I go confidently with my PCA and nothing. But yeah, what we heard from the back is that there is a physics understanding for this. It's called Wilson loop. If you connect all the orange one, you get this snakes here. And if the snakes aren't broken, you are in a ground state. And if they are broken, you are in a higher temperature state. But the thing is that if you wouldn't know the Hamiltonian, you wouldn't know about this whole connecting loops thing, it would be pretty hard to look at these configurations and distinguish the transition like in this easy, beautiful Ising model. And so it turns out that it's not so easy as just take a basis change, which by the way is linear, and a lot of these problems are nonlinear, that does this thing. But maybe we can use a more sophisticated method, that it's not just a simple clustering technique, we can have some more general function fitting approach to solve this problem. And, this is how neural networks kind of obliquely come by. Neural networks have been around in machine learning for a while now, basically since like 2012, 2015, like we had a lot of this kind of image classification, image recognition. So prototypical task for machine learning would be, I have characters from these two movie franchises, and I want to make a neural network that will distinguish the two, right? And then I will assign Star Wars one label, Star Trek the other label. And for the problems where maybe a simple linear clustering method doesn't work, nothing stops me. And this was super profound idea by Juan Carrasquilla and Roger Melko back in 2017 to just say, Leia is a low temperature phase, Spock is a high temperature phase, and we go as we would. Now we are treating our spin configurations as classes for image classifications, and we can just do something like this. And then we have a thing that is a machine learning model that maps these configurations on these two classes, but it does some physics task instead of just doing some we rotate the axis like this. Now, at this point of the talk, we could just say, machine learning, it does something, it's a computer science, we will not deal with that, and let me just show you what it does. Maybe when I was thinking what would be productive for today, maybe we can learn together what these machine learning models actually do, so we can also step away from some of this super intelligent killer robot fantasy and be more grounded in that we are just actually fitting some function. So why we even have this term machine learning? In, let's say, traditional programming, we have some input, we write a program, and this gives us an output, right? For example, if I want to simulate this Ising spin configurations, I will write some Monte Carlo sampling algorithm that will create them for me. Sort of different philosophy is if I know what is the desired result that I want, but the thing that I am trying to find is the program. Meaning, I have a lot of pictures from Star Wars and Star Trek, or from low temperature and high temperature phase of the Ising model, and I know that there is two classes of them, and I want to create a map that maps, Leia on Star Wars, Spock on Star Trek, always, and will generalize well to other instances. And so this is what generally this term machine learning means. Now, there is like an infinite number of machine learning models, but in the end, neural networks are this like OG thing we are usually thinking about. So let me explain that one. And it's also where this sort of brain analogy comes from, but we can call it neurons, but actually it's really, really simple. So we have these neurons, the colorful balls that are organized in the layer. Inside of each of the neurons, very simple thing happens. I do a linear combination of the weights that are coming from the previous layer and add a bias that is stored on that neuron. So I am just doing a linear combination plus constant, normal linear algebra stuff, nothing crazy. Then I do one more thing is that I need to multiply it by some very simple nonlinear function. This nonlinear function, they are fixed per layer, and it's something simple, like tangent hyperbolic, for example. But it's nothing more than this, just a little bit of linear algebra. And then I have many layers of these, and in the end, I have this object that is parameterized by the value of these connections, the weights, and the numbers B, the biases that go into doing this linear combination. And that's really it. So to find the program, we now have this object that for reasons is good at fitting data. And the only thing that we need to do is to find these weights. And once we found them, we constructed a program that is custom-made for this high temperature, low temperature classification, or tuning your gate, or predicting your Hamiltonian, or whatever else you choose to do. So let's now really understand how this actually works. So I'm not like just talking about it, but we actually calculate it together. So now is the, if you brought a notebook now or your iPhone calculator, now it's time to take it out. Let's take super simple neural network. We will have two neurons on the input. They will have values of your input data. So for example, now x1, x2 could be spin up, spin down, +1, -1 of this Ising model. Then I have 4 weights that connects it to the 2 neurons in the second layer, Q1, Q2. And then I just have 2 weights, A1, A2, that connect it to the output Y of the network. Super simple 5 neuron thing. So going with this philosophy of the linear combination, I just explained, if I want to do the linear combination on every neuron, I just need to multiply this matrix, right, with this input vector. Then I multiply it, I even write you all and I get what's stored on the neuron Q1 and Q2. So now let's again play another game. I give you numbers now for the weights and for the input. The input will be 1, 1, for example, spin up, spin up. The weights, I initialize them or it's already trained, it doesn't matter. They have these values 2, -1, -2, 2. And then I am asking you what is a Q1 and Q2. Thank you, very good. See, it's super simple, like it's a, you feel like I'm trying to trick you, but I'm really not. Okay, second layer is even simpler. Now I have just these 2 connections, so I'm just multiplying a row vector, column vector. I get this, so what is Y now? If I tell you that A1, A2 is -1 and 2. Perfect, we did it. We just did a forward pass through a neural network. You know, super easy. Okay, now what we need to do to find the program is to optimize the neural network, meaning adjust the weight so it would do what we want. Let's say for the sake of argument that just making the output Y as small as possible already does that. So if we have output and on the other axis is all the weights of the network, we need to walk, if I know the gradients, I can just walk my ideal path to the minimum, and when I am there, I solve the problem. So in the end, what I need to figure out is how the derivative with respect to all my variables influence the output, right? So how do we get them? We will just differentiate. But we will differentiate in a smart way. There is a chain rule that I'm sure you know. If I want to go deeper into the network, I need to calculate the derivative of the output with respect to one of these weights. So what I need to do is to first calculate the partial derivative with respect to the previous layer, and then to calculate the partial derivative of the previous layer with respect to the variable that I want. Now comes the trick. Because I made you do this offensively silly calculation in a forward pass, we actually calculated those things analytically. We don't need to differentiate anything numerically. You know, and you can even read it from the graph here, that Y is A1 Q2 plus A2 Q2. So you know that dy dq1 is A1, and we know a value of that because I told you what it is. The same with dq, d, and so on. This second thing is even 0, and you can immediately see it because Q2 and W11 are not connected on the graph. So if I zoom in on the neuron, what I am going to keep track of is that I have neuron Q1, 2 weights coming in. Here I am storing the local partial derivatives. And to solve this problem that I presented to you right now, I just need to take a value of this partial derivative, multiply it with the value of the A1 that I knew from the forward path, and I'm done. And so in the end, whatever I want to extract from the network to minimize some objective, I just need to keep track of these local partial derivatives and combine them in the right way. And this is the core of something that is called backpropagation algorithm, which is the thing that makes these models fit the data so effectively. There is 2 things I didn't mention. As I was saying at the beginning, we just don't do this linear algebra. There is some nonlinear function, because if we just do this linear combinations, we cannot approximate arbitrary functions, right? We could only approximate linear problems, and that's not very interesting. So I remove the nonlinear function, so you have an easy time multiplying and differentiating, but it would be just the same with tangent hyperbolic in front of it. And the second small thing is that the output of the network itself is not a good loss function. You need something that will measure the distance to what you want. So for example, a good idea, if we again take our 2 friends and they will have 2 different labels, and the network will give us an output that will be a probability distribution between these 2 labels. It's probability Spock, probability Leia. A good loss function is, for example, this categorical cross entropy, one distribution times the logarithm of the other. That's just a function that measures the difference between 2 distributions. Maybe on the lowest line, I even wrote it up. We don't have to calculate it now, but if you sit down and substitute these labels into the loss for Leia and loss for Spock, you will immediately find out that the pink probability distribution has to be same as the label to minimize the loss function. And that's exactly the goal, right? So if we put all of that together and we come back to this problem, we have some data that is available. And Giordano made some good point that this labeled data is not always available, and that's a problem in itself, and we will come back to that later. But for our purposes now, I can just sample from the Ising model, label it with some labels that I use to generate those samples, the temperature, and do this classification with them. Another thing about this is that programming-wise, this is like as simple as it gets. To do this classification task that I showed you on a previous slide, you just need this 5 lines of code and no more. If you want, you can go straight to my course week 2 and go shift enter on it and make your own neural network. So maybe it's again not some, super intelligent thing taking over the world. It's just a small model that is fitting some data very well. And so if you would go to this notebook and do the exercise that is there, you can plot, we have these 2 neurons that is predicting the distribution between this low and high temperature phase. You can plot the value of those neurons as a function of the temperature. And what you are going to get is this plot, that one phase has a probability 1, then it's dropping, and then it's almost 0, and vice versa. And huge plot twist, where do they intersect? Exactly at our 2.27 old friend, where the phase transition is. So again, I can plot the values of the neurons as a function of external variables. I can play with them and find the phase transition the similar way, like is the old school normal physics way. So then what can we do with these networks? If we can do this, maybe we can do more. So the good news is that there is many applications in quantum physics and quantum computing, and this is something that my group has been working on. I think for today, I want to group the main applications into the 3 categories that I care about the most right now, but there is array of many other things that one can do. One is something that you hear me in QuTech talk about all the time, and that's the control and tuning. Devices are noisy, sometimes at different stages of design, tuning, operation. It takes a lot of human work. So the question is how much of that work we can automate away so you don't have to do it. The second, the slightly abstract one, is like if you measure a lot of data and maybe you would want to know what's a Hamiltonian that is an effective model of your device, or what kind of time evolution did you just simulated, or was your gate precise enough? There's this kind of learning physics. That's just a slightly more complicated way of this Ising classification that we showed. And then the most, abstract topic is that we can use neural networks directly as approximations of the wave function. So far, I was telling you I have some data, I have map, and I go somewhere, but wave function is also just a function. So then maybe I can use the network to approximate it directly and just see what happens. So what all these applications, even though tuning up a 2-qubit gate and doing variational Monte Carlo are two super different things from a physics point of view. From a machine learning point of view, all these things are kind of the same because it always goes measurements, they go into some fitting model, and then I'm predicting what I want. It can be a control parameter. It can be a Hamiltonian parameter. It can be expectation value of my wave function. Depends what you want to do with it. And of course, there is a lot of details that goes into the design and architecture and training of these models that for all these different applications are very different. But the underlying principle is kind of just this. And so let me now give you just a sort of superficial example in one of these categories, so you get a little bit of flavor of the type of contemporary problems we are working on. So if I start from the most abstract one, the main thing by solving hard problems in condensed matter or anything quantum and why we are all here is kind of, the 2 to the n scaling of the wave function, if I would talk about it like theoretically, right? If I have n spins and I want to describe them exactly, 2 to the n numbers. Always, so I don't know, either we need a quantum computers or we need some super efficient numerical method, but that's a problem that is in the core of this, right? And then if you are a numerical person, you spend maybe last 80 years thinking about this problem very hard, and there is many examples of how to approach it. You have this old school thinking about it very hard scientists making physics motivated ansatz. You have tensor networks, which are entanglement based, and the similar like you would any of these, you can just use a neural network as a similar variational ansatz. This is the same picture that you've been seeing all along. It just looks slightly different. I just have a 2-layer neural network. The connections, the yellow and the highlighted blue ones are weights. The gray thing is the biases on the neuron. The same thing as always, except now I took this exponentially large expansion in the wave function in the basis. I take the amplitudes and I parameterize them by the neural network in a way that the number of these trainable weights and biases will scale polynomially and not exponentially. And then I can just treat it as any other variational ansatz, stuff it into some expectation value and, for example, calculate the ground state energy of your system. Or I can do time-dependent variational principle, whatever you like. So in the end, if you have a Hilbert space, your neural network is kind of covering some point in the Hilbert space, and you are hoping that you can engineer the architecture just so that your blue blob will actually capture the wave function that you want to express, but in a number of numerical parameters that you can actually do on a classical computer. Problem with that is that useful quantum states are often extremely hard to approximate. For example, toric code states and any other, all of these error correction states, and it is like a complicated string orders. They don't come so cheap with these variational methods. And so we've been working a lot in my group of making these neural network quantum states more expressive. We've been making them more physical with Agnes, and Tom and Arash are working on making very rigorous measures that characterize quantum resources that are actually stored in these neural networks. So we are not just throwing fitting problem on a physics problem, but we are actually making them more expressive to describe the physics. If we move on to the second, slightly less abstract category, it would be the learning the physics to some degree of your problem that you have. In the end, all of these things boil down to some kind of workflow that looks like this. You can have measurement. It can be any measurement. This is example from the project we did with the ultra-cold atom groups where we have this occupation parity snapshots. But you can have your expectation values. You can have your parity readout, doesn't matter. You have this data set, and then you want to feed the data set into the neural network, and you want to train it to predict your Hamiltonian parameter, your phase, your noise profile, stuff like this. Two things maybe I want to highlight here. So on the ultra-cold atom size, which is now again like very, very popular topic, we few years back worked on actually estimating Hamiltonians really, really precisely in a scalable way with a very small number of measurements. And more QuTech topic is that together with Qubit Research Division, we built these estimators both theory and experimentally on learning the Hamiltonians of the Kitaev chain. Small anecdote about that. I think David is not here. He will forgive me, hopefully. The neural network actually identified the measurements that had a wrong experimental label correctly. So we ended up actually 100% classifying the correct side of the Kitaev transition with the neural network that Ruben was working on. And the final, most like down to earth thing, and for this topic I prepared actually very little because I feel I'm talking about this a lot in all the different work meetings that we have, is this idea of control and tuning. Machine learning is not a new contribution here. Like it was here at QuTech that people did non-machine learning things to automate operation of spins. When we started this project, we were thinking about this like, Leia and Spock style, as you heard me talking throughout the talk all the time, except that I take a patch of the charge stability diagram. I label it with something and I create some complicated workflow that tells me how to move to prepare a specific charge state. Or it tells me how to change some voltage, or you just go from the picture to some parameter that you can control. The challenge with that is that just thinking about it as a machine learning sort of engineering problem, it takes the interaction from the device out of the context. So there is a very clear limitation to this. And now we come to the point that Giordano mentioned all the way at the beginning. Unless I can force someone to actually prepare these labeled data sets so I can just train my models however I like, this is not going to work. And I did that in the past. There was people in Klaus Enslin who very generously labeled a lot of graphene and HBN and other flakes for us so we could make a 2D flake identificator program. And luckily that worked very well, but it doesn't scale to every problem. And so nowadays, what I am much more excited about is to make algorithms that actually run on your measurement PC and directly interplay with whatever you are doing, whether it's initial tune-up or tuning up your gate or optimizing your measurement. I don't want to talk too specifically about concrete application here, but maybe I just want to highlight this shift that hopefully this also helps with. We don't need to wait until all the qubits are, perfect and exactly the same frequency and fabrication work out perfectly and the initial frequency finding work out perfectly and all the gate tune-up. At some point, separating these things, I think actually does more harm than good. And then it's funny to think about at how many layers of your imagined stack you can actually incorporate this feedback loop just on your measurement PC and just train it, so to speak, as you are doing initial tune-up of your device. With that, looking ahead, so yeah, I think all that I wanted to say in this talk is this. There is so much hype and sometimes we develop like so much trust that we go to like ChatGPT and be like, what is this super complicated thing? Will you tell me something I didn't know about it before? And then the question is, I mean, should it know? Is it reasonable that yeah, just because it can predict the next, like a high probability word in your sentence, it doesn't mean there is no, it doesn't mean that there is some super profound understanding, right? So if we more think about it, like we have this super flexible ansatz that can fit really complex data set, but they can fit them like super, super crazy, surprisingly well. And you don't have to make a tailored algorithm for every problem. To some degree, I mean, there is this questions of architecture and training, but in the end, sometimes you don't need to know the answer to do the thing. You can just take the data and see what comes out. And this kind of more experimental approach is very appealing to me. And so I hope I showed you some example that actually many challenges in quantum have this kind of general framework that we can apply this thinking to, that we can work together towards solving it. In the end, really just keeping track of those partial derivatives. Thank you.
I just wanted to ask if you could elaborate about the not having enough data, so the models that data do something. What are we going to do with it?
Yeah, great question. Thank you, Priya. So there is a lot of this experimental things of the work that is already done that I was mentioning ended up working because of something called pre-training. For example, with the KitIF thing, I am super aware that the experimental system that is in the lab is like so much more complicated than the simple Hamiltonian that we can write. But what Ruben and David and Alberto and collaborators did was like, okay, we just generated data from the simple Hamiltonian. This is numerically feasible, so we do that and we pre-train the model on that. And then we just ask our experimental colleagues to be nice to us and only measure for a couple of days. And then we retrain on the experimental data. And generalization from this has been really exceptional. And this philosophy actually worked in many different approaches. And in the end, from a computer science point of view, it's also a reason why this large language model generalized so quickly to the new task. Because if you have a robust base model, it actually ends up working. And so it turns out that from first principle, simple physics-based models, we can build the robust base models and retrain them just a little bit. That said, we are talking about this as a community, like building up some big shareable data set, so you don't have to have a 24 access to dilution, which is something that is central goal for the next few years.
First. Go ahead, Peter.
So it's the control and tuning, and then there's the Hamiltonian learning. The example you give for Hamiltonian learning is basically to classify whether you're on one side or the other of the transition. Is it then, so Hamiltonian learning to me also sounds like you're actually trying to learn what the parameters are in the Hamiltonian, which is not yet the same as the classification of what the graph state is or something. So let's see that. And then the other question is, if I interpret Hamiltonian learning the way I just did, which I'm not sure if that's how it's intended, it looks very close actually to the control and tuning.
Great question, thank you. So I simplified significantly on the Hamiltonian learning. There, what we did was actually to learn the parameters of the Hamiltonian. Specifically, we really had to learn the ratio between these two main tunneling events in that experiment. And somehow that worked much better going via the Hamiltonian route than trying to directly classify those data because they are somehow noisy. So for us, it was like, look at the charge stability diagram and tell me if I am more on an elastic co-tunneling or the Andreev reflection side. But indeed, in that experiment, as you are saying, they are very like intimately connected because there are experiments like the ultra cold one where we just learning the Hamiltonian to the sufficient precision was a success and end of the story. In this project, we learned the Hamiltonian to the precision that we wanted, but then we use that knowledge to connect it to the stochastic gradient descent to if I'm on the slightly on the left of the transition, I should shift my voltage like so. If I am on the right, and then we use it for the actual tuning thing of those Pullmans-Majorana mid-gap states. So indeed, they don't need to be separate, but to me, fundamentally just saying change voltage or actually learning what is the underlying physics model, they are slightly different conceptually, I would say.
Yeah.
I had maybe a question along the same lines. So in your example, when you, for example, do automation and control of maybe a cubic system, so the goal there is to feed forward. Essentially, you facilitate an operation and tuning. My question is, are there efforts to actually use the knowledge that you gain in doing that tuning to actually feed back to understand what is the cause of disorder, imperfection, and so on? Because you end up with a lot of data. Is it useful for feeding back?
Yeah, no, thank you for this
How are
question.
people doing it actually?
Yeah, so for me, this is something that I want to do very much. There is a lot of practical things that makes this project challenging. But for example, in actually my very first machine learning project with our collaborators in Oxford, I was just fitting the noise amplitudes on the different noise channels for a gallium arsenide quantum dot, right? And had I had more time in my PhD, then I can use that knowledge as a concrete input in tuning. So there is some efforts, but just infrastructurally. And I think this is why actually being now part of QuTech is such a great opportunity, because actually then use this knowledge to have, okay, now there is a concrete experiment in the fridge and we can in a real time update, because without that feedback loop, I can write a theoretical paper how it should be done, but if I don't get a feedback data to test it, then I am limited. So in that sense, I think there hasn't been as much progress as I would have liked, but it's really something I'm thinking about a lot. Thank you for the question.
Thank you. Also a very nice explanation. When you approximate the quantum state, when the Hilbert space grows, the data set also grows. Have you encountered this problem, and how did you solve this?
Yeah, great question. So the good news about this is that we are not doing anything super new, in a sense that this variational Monte Carlo community exists. They just work with a different ansatz. And all of this, of course, in this Monte Carlo techniques, you don't have analytical proofs, but there is a good feeling for how much you need to sample if you are in a nice phase, how much you need to sample around criticality. So in the end, what this comes to is that we read some papers from the 70s, take that as a ballpark estimate and go from there. And usually what we can do is that with a super reasonable number of samples, are in thousands, tens of thousands absolute bursts, and polynomial number of trainable parameters, we get a really good results on the energies, for instance. Great question, thanks.
Yeah, so in computer science, at the moment, it's explainable AI.
Yes.
Turning the question around, can you say anything about investigating these existing neural networks or large language models or whatever as physical systems, and try to observe, what are phase transitions, how does it behave, and anything about it?
So first thing I will say that this is definitely outside of the core of my expertise. There is a research of Lenka Zdeborova at EPFL, and what she does is that she takes small models and tries to reproduce this phase transition concepts of the spin physics with those. So there is more like a mathematical effort on this. At the same time, it doesn't mean that we are satisfied with just training some black boxes. There is interpretability tools that are to some degree limited, but they can be very powerful. Like for example, this thing that I was showing, that the probability of the output neuron in the Ising as a function of temperature is the simplest version of that. I can plot my convolutional filters, I can calculate relevant correlations, and people are really working on this interpretability techniques a lot. Sometimes you immediately figure out, here my model was looking at the boundary and it found the edge mode, and sometimes the models are so big that it's hard. One thing I want to mention is quantum machine learning. there is a lot of drawbacks at the moment because it's nice, this partial derivative argument that I was showing, it doesn't work there. So the training is hard. But if you map your problem on a quantum system first, the 2 to the n goes to the n, and you are working with much less parameters, and you can just do things like plot correlators of your parameters, looking at stuff like that, and that the interpretability seems to be a little bit easier, but it's super, right now, as you say, is a hot topic. People are working on it. I think it's far from clear what will happen there. Yeah.
You can jump in the question here. So a bit of a naive question about neural networks. You have been touching upon these nonlinear functions. Could you tell us how does the shape of that function? Does it matter, or should have been a little bit more? Yeah.
So it turns out that you actually need to get this like a learning expressivity, you actually need just a little bit of the nonlinearity. So what people usually are picking are some functions that have like a lot of slope, like around between like 1 and 0. And so all of those functions like look like that, like it's kind of sigmoid or this tangent or softmax or something like, or ReLU, the one that is constant until 0, and then linear from that. And so I always tell to my students when they are worried about this, just pick a random one, and like changing the nonlinear function will not make or break your training. There can be some like very fine-tuning things, or sometimes you want a specific one that really renormalizes your distribution in a particular way, but they are more of a detail than a fundamental thing. So I always say just put ReLU everywhere, and then you see what comes out.
Maybe another quick question. How can you make sure that you are finding global maxima and not local maxima in all of this?
Oh, yeah, no, you cannot. So and this is the same with any like a probabilistic optimization technique. So then you just need to be super rigorous about your testing tests and going instance by instance, plotting your gradient profiles. We have to do all the normal things that other numerical techniques also have to do. Yeah.
Yeah. Thanks. Yeah.
Great, Rob. So for the Spock and Leah, so in practice, how many nodes of inputs would you use for the machine learning problem, and how many layers to get a good prediction?
So for the images, there is just some mediocre resolution, which actually ends up then being really big, right? Because if I have an image that is 200 pixels by 200 pixels, that's not great. So then what happens, and I didn't talk about it in this talk, the architecture doesn't look like that everything is connected to everything. You have this like a small modules that scan your image, and you train the same matrix of, let's say, 10 on the whole image. And then you do another matrix of 10, another matrix of 10. This is called convolutional filters. And when you train enough of them, you move to the next layer. So this idea that you have to connect all your 40,000 inputs to the next layer is not true. You first do this scanning and then you downsize. So for example, the simple model I was showing for this Ising, for a 40 times 40 Ising, if I take 2 layers between 20 and 40 neurons each, I'm good. Even fully connected. So a lot of simple problems will have like, I don't know, tens of thousands parameters.
So the first example, right? So you say you do this sort of convolutional step. 20 input parameters, 20 pixels, then basically.
Yeah, for example.
Process between 2 layers, they will train them, but what does training mean in this case? Is it trying to really learn something, whether it's leaning towards layer or Spock from the 20 pixels? Or?
Yeah, it tries to extract what could be an interesting feature. Like for example, and sometimes what this interesting feature is sort of unexpected. For example, the old Star Wars movies, they have very particular color filter. And in the RGB scan, the convolutional filter will pick up on this and store that. Or it saw a lot of pictures of Leia, so it will look for like a edge of the like a round bun or something white. And so each of these filters will find something, and at some point you have enough of them. But this is, again, I want to emphasize, this is just me saying specific example. I cannot predict what they will learn, so I have to go in with a lot of hyperparameters and just fine tune the model. So it all comes together.
But the fine tuning already does use just 20 pixels. You say it leans towards, it starts to go towards normals. Like that's the feedback loop, or did it? Is
No.
that what you're trying to minimize?
So no, so there is not a feedback loop yet, but I have smaller numbers of weights that go into the following layer because I am scanning in this site a smaller weight. So I extracted something, and then that something.
I think you said certain, but I thought you said that there was already learning in the first step.
No, so it's not a learning in a sense that, okay, so so I will just finish my point. So I extract something, then I go to the next layer, and eventually those features of the convolutional layers, they get minimized like everything else we did, and they get optimized to extract some feature, but there is no feedback in this convolutional layer itself. I am just sort of pre-processing my image to not be just 40,000 times 40,000 matrix. I am just making the number of channels smaller, but I train the whole thing together. So yeah, I didn't mean to say that just doing the convolution there is no feedback. It's just the architectural choice, and then the whole thing gets trained in this backpropagation.
What questions?
Yeah, I think to an earlier question about approximating a wave function, you said that you need polynomial number of parameters.
Mm-hmm.
But doesn't that mean that the effective dimension of that data you're trying to learn is then polynomial as well, right? And in principle, it could be exponential. The Hilbert space could grow exponentially, right? And the complexity of the data could grow exponentially. So then to approximate an arbitrary quantum state, you still need an exponential number of parameters, right?
Oh, sure, right? If you throw at me your completely versed is some spin liquid transition, these methods are also going to break. It's just that for a lot of things, you can find a polynomial representation, it's just that it's very hard. And the standard way of doing it is that you build this representation on some knowledge or assumptions about entanglement, but we don't have to worry about that. So we have a sort of more freedom to put this polynomial representation together. But as you are correctly saying, the ground truth is exactly exponential. So it depends if I am able to tackle it efficiently or not. We need to try and see.
So quantum computers are still useful.
Yes. I just think that it's actually very interesting, right? Because it's powerful in some sense that I can, with a tensor network or neural network, simulate these experiments, and the result is exactly in the middle of all the error bars of the experimental thing. And I think this is very good and healthy for the both communities. So yeah, I am not trying to replace quantum computers, but I think it's useful to simulate them sometimes.
You've been talking about neural networks, and you also mentioned convolutional algorithms. So I was wondering, do you use always the same type of algorithm, or do you tailor it to a specific problem? And
Yes, so there is a huge zoo of algorithms, even like between neural networks, there is so many options. For example, when I talked about the Kitaev model, you could have noticed that there was some crazy contraption on the slide because the architecture can become very complicated based on the problem that you need. And then there is models that, like, nowadays you can call anything that meets this requirement. I am fitting the program, not hard coding it, is a machine learning. And then there is many, any clustering with flexible clustering parameters also meet that requirement. So I think with some experience, there is like benchmark problems that we already know are useful for a certain types of tasks. And then in my group, we usually just look at the data that we have and narrow it down to like 3-4 candidates. Then we try that, and based on what we get from those test problems, we decide what the actual method will be that we use.
Follow-up question on that. Can you use the current set of big models to find the right set of neural networks or the right set of algorithms to fit to a problem?
You say I use some external model to tell me what my architecture should be. Yeah, this is definitely a thing. In my experience so far, but I think already in 2 years from now, I can give much more positive statement. These things give answers, but sometimes you get some like peculiar architecture and you are like, wow, I wouldn't have thought about this. But then the loss function is just, 10 to the minus 10 better than what you would have done with your intuitive guess. So it is true that there is a local minima, but because the way your data gets fitting, the way there is so much flexibility, I am really a big believer for this, just like an intuition guided architecture. You will not go like super wrong with it. That's what I think right now. Yeah.
Curious, have you encountered issues with the Baron-Plateau effect in training on quantum systems?
Say again, what was the end of the in-what systems?
Yeah, the Baron-Plateau effect in the fact that optimizing a function has some really flat regions.
Yeah, no, this is definitely a big problem. Somehow right now I feel it's a bigger problem for quantum machine learning than for classical machine learning. There is not universal known solution to it, but there is all of these tricks like adaptive learning rates, like what size of the steps you do when you are navigating the network, combinations, different optimization algorithms. I didn't talk about this. I just tell you, you calculate a derivative and then you're done. But what you do with that knowledge of the derivative matters based on your landscape. So usually we actually look at the quality of these landscapes on a gradient structure. And from that, we can make some educated guess what kind of optimizer, what kind of learning rate adaptation structure we should use. So in the end, it's a lot of numerical groundwork, and it is definitely a problem, but it's not like unovercomable problem. Great question. Thank you.
Asking questions on Slack. Practical one. Yeah, how many of these famous NVIDIA H100 chips have you bought with your group, or do you have access to, or how did that work?
Great question. So 3 is the answer, and it's plenty actually for what we are trying to do. Like in the end, you can actually train, when you think about training specialized model just to tune up a gate, you need a lot of memory to train it. So for example, 3 H100s, but that's a lot of memory. And we very rarely try to attempt this kind of very general, like, I shouldn't even compare it to the GPT because the scale is so different. But yeah, the quick answer is that you can actually do really a lot with relatively little, but you need some GPU, just like a casual standard TU Delft PC is not very good for these tasks. But buying a slightly better GPU already gets you very far.
So basically, in practice, you order a PC with such a chip inside, or it's a completely different type of machine? Or?
So it's a different type of machine. For this, like a relay for the thing that I said with the 3, that was an expensive type of machine that is just the GPU that is being cooled somewhere here at TU Delft, and we connect it remotely. It's like a mini cluster that we are running. But we really just need for our most like a hardcore memory problems. For most day-to-day, I just need to, what you said, the first thing, I just need to buy like a better computer with some GPU that means the specific requirements that we need. It's scalable.
How does that relate to speed in terms of if you want to do some real time? Is that mostly for the training or for the actual?
Oh, great question. So in the end, if I simplify super much, the speed is really at some point limited of how many things I can process in parallel, and like the more memory is always better in this sense. But it's again like there is a way that you can like think about what you need, then train the first model. When it works, you can figure out how much you can minimize it to run on the go. So yeah, but the training is always the most expensive part, but it can also be done like maybe the pre-training is done on the TU Delft Blue cluster and we don't have to worry about it. So
Sorry, this is super vague, but do you see any fundamental limitations to using ML for physics discovery, using this approach?
and the limitations meet any limitations.
Or more like fundamental ones that are harder to turn on?
So maybe let me say like this. I think that the limitations are pretty much the same like for any other computational algorithm. I think that this field developed this thing like it's something else. We are doing something with the AI, but we are really not. We have this like a cool method, but it's not so different. It just adds extra flexibility to your toolbox. So I don't think that like, you know, maybe it would be super hard for me to fit some experiments if I wouldn't have this tool, but it's not that the properties of the tool will hit some super hard limit. I think what's a bit of a limitation right now, maybe back to the Leven's question, that it's not completely normal for the PC to be this kind of like a machine learning PC. You need to do something special. And then you always need to think about the hardware, about the memory. And so maybe what's like a normal computer will, I think, change over the next 2 years, and then we are fine. And I think that's the main practical thing right now. But from the methods side, I think there is no obvious problem right now.
Right, so we are fine now. So let's thank Eliška again.